Hi everyone from Climate Winds. I'm Mathieu Dacol, your data analyst, and we are gathered today to talk about the evaluation of machine learning algorithms for weather prediction in mainland Europe. So, as you recall, the objective you gave me was to use the machine learning algorithms for categorizing and predicting weather in mainland Europe. So, I'm going to focus on three different thought experiments trying to answer some of your questions. First one would be finding new patterns in weather changes over the last 60 years. The second, identifying weather patterns outside the regional norm in Europe. And lastly, generating possibilities for future weather conditions over the next 25 to 50 years. So, when we talk about the machine learning options that we studied for this presentation, we first tried out the random forest, meaning an ensemble learning method that constructs multiple decision trees and merges their result for improved accuracy and stability. We then have the hierarchical clustering. As you recall, we had already the k-means clustering from last study. Now we're moving on to a new clustering algorithm that builds a hierarchy of clusters by either merging or splitting them successively. We also went into some more deep learning algorithms like the RNN, the recurrent neural network, which is designed for sequential data, where connections between nodes form a directed graph along a temporal sequence, allowing it to capture temporal dependencies. We also have the CNN, the convolutional neural network, which is particularly effective for analyzing visual data using convolutional layers to detect patterns and features. And also we have the GAN, the Generative Adversarial Network, which is more a deep learning model where two neural networks, one generator and one discriminator, compete to produce some increasingly realistic synthetic data. Let's move on to the first thought experiment I suggest, which is finding new patterns in weather changes over the last 60 years. For this thought experiment, we'll stick to the random forest to analyze feature importance and identify key factors influencing weather changes. As data needed, we have the historical weather data by temperature, wind speed, precipitation, and all other relevant variables, meaning we don't need any other data than the one provided. The random forest had an impressive accuracy rate of 100% when each weather station was isolated, making it a strong foundation for understanding the key factors. While when we run it on the whole dataset and not on each individual weather station, we had still an accuracy of about 80%, which was really good. So as you can see on the medium graph, the feature importance for Budapest, for the example, we can see that the most important feature are precipitation, then max temperature, then mean temperature, and then global radiation. And it was really coherent from station to the other. Our second thought experiment is identifying weather patterns outside the regional norm in Europe. We could use for this one two algorithms, the first being the clustering hierarchical, to group weather patterns and identify mostly outliers and better understand the regional norms. And also we will have the CNN to analyze the spatial patterns in the weather data, such as satellite imagery or even webcam live images. So the data needed would be still the historical weather data, and we could add some satellite imagery or some regional climate data. As a visual, you can see the dendrogram from the hierarchical clustering, which was quite good at finding about 2 to 3 groups inside all the weather data. And the CNN that was quite good also at recognizing images with the labels. So it was a good classifying and recognizing image algorithm. We see it on the confusion matrix on the on the right of the screen. And for cloudy and shiny, um, it, it had a little misrecognitions, but quite few. But since both categories had many pictures of skies, so with some fine tuning, we could make the CNN work even better. And the last thought experiment would be by generating possibilities for future weather conditions over the next years. So with that, we would use more advanced algorithms like the GANs to generate synthetic weather data and simulate future conditions. We would then use also the RNN to predict long-term weather trends and patterns. For that, we would need data, the historical weather data, the climate models, and some social economic data as well. The RNN had a great optimization curve from about 5% to 70% accuracy with a simple Bayesian optimization. So it still has areas where the model struggles to differentiate between similar weather patterns, as you can see on the confusion matrix on the left of the screen. So Ljubljana was well recognized, then Düsseldorf also a lot, but afterward we don't even have the all 15 weather stations. So there is still a big place for improvement on the RNN, and we could still use it and gain a lot, mostly on the prediction and on the time series analysis. As for the GANs, we didn't try them yet, but it would still be a great algorithm to run on this thought experiment to have uh, just to generate even more weather data. So for the recommendations, I would strongly I would strongly recommend going for the first thought experiment, which was finding new patterns in the weather changes, since it's the most immediate one to implement and the easiest one to implement. So as a first step, we I would strongly recommend to use the random forest. Then let me suggest some algorithm implementation plan in order to have a follow-up of all of these technologies and make them work all together. So first, we would implement and optimize these random forest models for each weather station. We then develop initial hierarchical clustering system to understand more regional norms. Then we could deploy the CNN from pattern recognition from satellite imagery. We could then integrate all these RNN for temporal pattern analysis. On top of that, we could develop some initial GAN models for weather simulation. Then create some composite models combining even multiple algorithms, and to finally implement real-time prediction systems. And even then create some visuals and dashboard follow-up, etc. As for the data requirements, we need some extended historical data, namely on the altitudes, which was something a bit missing in our data sets, the wind directions also, and the atmospheric pressure. We would then need to seek some satellite imagery archives, or even up to date. Also, the ocean temperatures around Europe could also be really useful, and also the urban development and land use changes, so that we know how much forest there was and will be around that. So that's it for the recommendations. I hope I was clear on all of this study. Thank you very much for your kind attention. And if you have any questions, just please don't hesitate just to contact me for some follow up chat. See you until next time. Bye.